The sun has just done something quite frightening. A massive hole has torn across its surface, releasing a stream of plasma toward Earth. And at that exact moment, the interstellar comet Atlas vanished from every telescope. And at the same time, Mother Earth experienced an earthquake. Now, the question on everyone's mind is simply what happened. Was it destroyed, or has it transformed? And what will it look like when it reappears? If it ever does, as one comet fades from view, another one flares into brilliance. Comet Lemon, an icy relic older than civilization itself, is soaring across our skies. We will tell you why the next 2 weeks are so very important. Meanwhile, in China, physicists have achieved something that sounds like pure science fiction. It's an unhackable communication network, a perfect tattletale. And don't blink, because before we finish, we'll reveal the cosmic dates you do not want to miss, including one that no one is talking about but should be. If these mysteries leave you as unsettled as I am, don't. Just watch, take action, press like, and hit that subscribe button, and continue to follow along as these stories unfold in real time. Leave a comment letting us know where you're watching from. What is your local time? And answer me honestly. Do you believe that we are being told the whole truth about these world-changing discoveries? And if you want to help this community grow, please share this video on Facebook, Reddit, or even in your group chats. Every click is fuel for the search. We can continue to pursue these stories. So, thank you for standing with us in this search. Part 1. The Disappearance. The sun has just done something deeply unsettling. October 2025 arrived with a cosmic alarm bell, one that most people never heard. Scientists monitoring our star observed, with an unease that grew by the day, when a coronal hole, a giant transequatorial one, tore across the sun's surface, a fissure in the sun's magnetic field, looking like a wound, leaking invisible energy into space. This was not typical solar activity, the kind that creates beautiful auroras and might disrupt a few satellite signals. This hole was exceptionally large, spanning regions of both the northern and southern solar hemispheres simultaneously, a configuration that rarely occurs, and with consequences we are only just beginning to understand. The solar wind pouring through this tear in the sun's magnetic cloak reached speeds of 700 kilometers per second. To put that into perspective, imagine a hurricane, where every particle of air is moving at nearly 1,500,000 miles per hour. This stream of charged particles, protons and electrons stripped from their atoms, hurtled directly toward Earth like a cosmic fire hose, aimed squarely at our planet's magnetic field. The alignment was perfect, almost suspiciously so. The magnetic polarity of the solar wind matched Earth's field orientation in the exact configuration needed for maximum coupling, that is, the most powerful energy transfer possible, possibly from the sun's breath and from the influence. Geophysicists rushed to predict the impacts. Power grid operators received warnings. Satellite controllers prepared for possible malfunctions. Aurora hunters packed their cameras and headed north, knowing that this type of solar event would paint the sky with indescribable colors. But something else happened at that very moment, something that would turn this solar event from a mere episode of ordinary space weather into a true cosmic mystery. Comet BAI Atlas, the interstellar object, only the second to be confirmed ever detected in our solar system, had vanished behind the sun. A moment before, it was still there, a faint streak of light moving in its orbit, originating from another star system, carrying ice and rock formed within distant clouds, around a sun that we would never see. It disappeared into the sun's glare, swallowed by the overwhelming brightness of our star, invisible to every telescope on Earth. And in space, this timing was impossible to ignore. Earth's magnetic field was being battered by the fastest solar wind, in a fierce assault not seen for months, and at the same time, our interstellar messenger, our only accessible one, slipped into darkness, right behind the very source of that assault. Scientists are cautious people, trained to avoid jumping to conclusions, drilled to repeat the mantra. That correlation does not equal causation. They weighed their words carefully. When reporters asked whether these events could be connected, then the earthquakes began. Multiple powerful magnitude 7 earthquakes struck different regions of the Earth. Within just a few hours of the solar wind's arrival, seismographs registered the violent shaking, the sudden release of tectonic energy that had been building up for many years, perhaps for decades, in the stressed rock beneath our feet. The tremors were not unexpected in a statistical sense. On average, the Earth experiences about 15 magnitude 7 earthquakes each year, but for several of them to occur so close together in time, coinciding with a major solar event and the disappearance of the comet's tail into the star, activated something in the human pattern recognition system, that ancient part of our brains that seeks connections, that demands meaning from coincidence. Could the sun's magnetic assault on the Earth somehow trigger seismic activity? The mainstream scientific consensus says no, that's not how earthquake physics works. Tectonic plates don't care about magnetic fields or the solar wind and slip according to the laws of rock mechanics and accumulated strain energy. But there are other voices, researchers working on the fringes of geophysics, who point to statistical anomalies in the timing of earthquakes. During periods of solar maximum, mechanisms involving ionospheric coupling, or subtle changes in the Earth's rotation speed. These ideas have not gained traction in the peer-reviewed literature, but they circulate in conference hallways and online forums. As for the possibilities, rest assured that mainstream science has not yet disproven them to everyone's complete satisfaction. However, the comet is where the real mystery lies. 3I Atlas received its designation as the third confirmed interstellar object discovered passing through our solar system. The first object was Oumuamua in 2017, the strange, elongated object that tumbled through the inner solar system and exhibited an acceleration that could not be explained entirely by the usual outgassing of a comet. The second object was 2I Borisov in 2019, which looked and behaved like the comets that we are more familiar with, a familiar ball of ice and dust, obeying predictable physics. 3I Atlas was discovered in 2022, tracked as it fell toward the Sun on a hyperbolic orbit, moving too fast to be bound by our star's gravity. It was clearly a visitor just passing through, on its way back to interstellar space. These objects are incredibly precious to science. They are the only samples of material that we have from other star systems, at least until the time when we develop the technology to send probes to nearby stars and returning to physical samples, something that will not happen in any of our lifetimes. Every photon of light that we gather from an interstellar comet carries information about the chemistry, about the composition of protoplanetary disks around other suns, about whether the processes that formed our solar system, universal or unique. When Comet Atlas disappeared behind the Sun, we lost the ability to collect that data, at least temporarily. The question haunting astronomers now is simpler and more troubling than any speculation about solar wind or comet quakes. When Comet Atlas emerges from behind the Sun, if it emerges at all, will we recognize the object that comes out? Did the Sun just swallow our interstellar? Could the intense heat and radiation and the magnetic turbulence near our star have possibly reshaped, broken, or completely vaporized it? And the answer could overturn everything we thought we knew about these strange wanderers. Part 2. The Traveler We Lost. The story of Comet Atlas begins, like most other comet discoveries, with patience, with automated telescopes scanning the night sky night after night, searching for anything that moves against the background of stars. The Atlas Project, short for the Asteroid Terrestrial Impact Last Alert System, robotic telescopes distributed across the globe, designed primarily to detect asteroids that could pose an impact threat to Earth. But the telescopes do not discriminate. They capture anything that moves, including comets, and in the early months of 2025, they captured something extraordinary. The object first appeared as a faint smudge in the images from the observatories in Hawaii. Follow-up observations from other facilities confirmed it was moving, and moving fast. Orbital calculations revealed the telltale signature of a hyperbolic orbit, an eccentricity greater than 1, which meant the object was not bound by our sun. It came from somewhere else, and after approaching our star, it would depart, heading back into the interstellar cosmic ocean. Its orbital energy was inconsistent with a native object of the solar system. This was an interstellar object. The astronomical community quickly mobilized. Telescope time, always scarce and competed for months in advance, was suddenly allocated. Spectroscopy, the analysis of light reflected or emitted by the comet, became a priority. What was this object made of? Did it contain the same mixture of water ice, carbon dioxide ice, and organic molecules characteristic of the comets, born in the solar system, our very own? Or would its composition reveal an alien chemistry, a ratio of elements indicating formation conditions around a different type of star? The initial data suggested something puzzling. Her brightness. Atlas was not behaving quite as astronomers expected. Comets typically brighten as they approach, the sun following a predictable curve related to the increasing sublimation of its ices. As the sun's heat intensifies, water ice begins to sublimate, turning directly from a solid to a gas as sunlight warms the surface to about 200 degrees Kelvin. Other volatile substances, like carbon monoxide and carbon dioxide, sublimate at even lower temperatures, creating activity at much greater distances from the sun. The light curve of Comet Atlas showed periods of flattening, where the comet didn't brighten as much as models predicted, followed by sudden jumps in brightness, suggesting distinct outbursts of dust or gas. The coma, the fuzzy cloud of gas and dust surrounding the nucleus, seemed unusually faint in some observations. Dust production appeared to be lower than expected for a comet of its size. Some researchers, however, speculated that the nucleus might have an unusually high density, more rock than ice. This would explain the weak activity, while others suggested the opposite, that the nucleus was extremely porous, almost like a rubble pile, held together by weak gravity, and that this structure was causing the sublimation of ice in bursts of unpredictable eruptions, rather than being stable. Then there are the non-gravitational forces, as comets do not follow a purely Keplerian orbit, which is determined solely by the sun's gravity. As ice sublimates from the nucleus, it creates jets of gas, acting like tiny rocket engines, slightly off its predicted path. These non-gravitational accelerations are small, but measurable, and they create uncertainty in predicting exactly where the comet will be at any given moment. For Comet Atlas, these perturbations were particularly difficult to model. The orbital calculations were continually being refined. The error bars kept shifting, and astronomers grew more and more uncertain about exactly when and where the comet would emerge from behind the sun. Some observations had hinted at the possibility of fragmentation before it vanished. Cometary nuclei are fragile things, loosely bound collections of ice and rock that can fall apart under thermal stress or tidal forces. When a comet fragments, it often produces a string of smaller pieces following similar orbits, sometimes visible as multiple condensations. Images of Comet Atlas showed asymmetries, which might occur. These elongations could indicate that The nucleus was beginning to disintegrate. If the comet had fragmented before it disappeared, the question became even more pressing. What would emerge from the sun's glare? Perhaps not a single object, but a stream of fragments, or perhaps nothing at all. If the fragments became too small to detect, the comparison to a previous interstellar visitor was inevitable. Oumuamua, the first discovered interstellar object, was never confirmed to be a comet. It showed no visible coma, no dust tail, nothing that could definitively identify it as an icy body. However, it accelerated away from the sun in a way that could not be explained by gravitational forces alone. The most likely explanation remains cometary outgassing, but of an exotic volatile substance other than water, possibly carbon monoxide or molecular nitrogen, substances that would sublimate without producing visible dust. Alternative explanations, from light sails to alien probes, have captured the imagination of the public, but found little support in the scientific community, who deal in evidence rather than speculation. 2I Borisov behaved more like a familiar comet, with a proper coma and tail and variations in brightness that reasonably matched standard cometary models. Its spectrum revealed water vapor and carbon monoxide, a chemistry similar to what we see in solar system comets. This was reassuring in a way. It suggested that planet formation around other stars follows similar rules, producing similar objects. But Borisov also showed signs of fragmentation near its perihelion, its closest approach to the sun. Images captured what appeared to be a small fragment breaking off the main nucleus, a reminder that these interstellar travelers do not always survive their trip through the inner solar system intact. Now, Bay Alas is following a similar path, diving towards the sun, and we lost track of it at the worst possible time. The geometry of solar conjunction. When an object passes behind the sun, as seen from Earth, creates an observational gap that can last for days or weeks, depending on the object's orbit and brightness. For A and Shia, faint comet, it had already shown signs of unusual behavior. This gap became a black box, a period of time where anything could happen, and we would have no way of knowing. The comet could be disintegrating. It could be brightening significantly. It could be intact and too close to the sun's glare to be seen. We would not know until it emerged. If it emerged, models had tried to predict this. What would happen? Based on an assumed nucleus size and composition. If the nucleus was large and mostly rock, thermal models suggested it would survive very well with minimal mass loss. If it was small and icy, the heat near perihelion could completely vaporize it, leaving nothing but a dispersing cloud of gas and dust. The uncertainty in the nucleus size was huge, ranging from a few hundred meters to several kilometers, a factor of 10 or more. And that uncertainty propagated through every predictive model, turning forecasts into guesswork. The phrase that astronomers kept using was the invisible interstellar traveler, somewhere beyond the blinding glare of the sun, hidden from every telescope that humanity has ever built. An object from another star system was surviving or dying, and we could do nothing but wait and wonder. What would emerge when the geometry finally allowed for observation again? The wait felt like a millennium, compressed into days. Part 3. Solar wind meets alien ice. The sun is not a gentle thing. We think of it as our benign star, our life giver, the warm light that makes Earth habitable. But up close, the sun is chaotic violence, a roaring ball of plasma, where temperatures reach millions of degrees, and magnetic fields twist into energy-storing configurations. Like loaded springs, when those springs snap, the consequences can be catastrophic for anything nearby. The coronal hole that opened in October of 2025 was one of those events that worried solar physicists. Coronal holes are regions where the sun's magnetic field opens out into space, rather than looping back to the surface. These open field lines act like highways for the solar wind, allowing plasma to escape into the solar system at high speeds. The typical solar wind speed is about 400 kilometers per second. The outflowing wind from this particular coronal hole was moving at 700 kilometers per second, nearly double the speed, carrying more momentum, more energy, and more potential for disruption. When the solar wind at that speed encounters a comet, the interaction becomes complex and violent. Comets are not magnetically shielded like Earth. They do not have a magnetosphere to deflect the charged particles. Instead, the solar wind impacts directly into the coma, the cloud of gas and dust surrounding the nucleus, and strange physics comes into play. The gas in the coma is weakly ionized by the sun's ultraviolet radiation, creating a population of charged molecules. These ions react with the magnetic field carried within the solar wind. The magnetic field lines become frozen in and drape over, like a cloak, resulting in a magnetotail, a structure formed by the magnetic interaction between the solar wind's magnetic field and the ionized gas from the comet. This tail can stretch for millions of kilometers, downstream from the sun, glowing faintly in the light of carbon monoxide, ionized, and other molecules. The tail is not a passive structure. Disturbances in the solar wind cause the tail to wave and ripple. Disconnection events can occur, where the tail breaks off completely and a new one begins to form. These interactions are visible from Earth with the right instruments, and they provide clues about both the solar wind conditions and the comet's rate of gas production. When a comet encounters an extremely fast solar wind, while already stressed by the intense heat of the sun near perihelion, history provides some sobering examples. Comet Eisen was discovered in 2012 and was predicted to become spectacularly bright, disintegrated during its close pass by the sun in 2013. Images from solar observing spacecraft showed the comet entering the perihelion region as a bright object and emerging as nothing but a dispersing cloud of dust. The nucleus had apparently broken apart completely, unable to withstand the thermal and tidal stresses. Comet Lovejoy, a sun-grazing comet, passed within 140,000 kilometers of the sun's surface in 2011, somehow survived despite the predictions that it would be destroyed. Images captured the comet's tail, stretching for millions of kilometers. After perihelion, fueled by the enormous production of gas from the superheated nucleus, Lovejoy's survival was unexpected and has not yet been fully explained. Some combination of its nucleus size and structural integrity allowed it to withstand the heat, which should have completely vaporized it. It is not passing close to the sun, like those extreme sun-grazing comets, but it is entering a region where the sun's influence becomes dominant, and it is during a period of unusually intense solar wind. The question is whether the combination of stress factors, thermal, plus heating from radiation, plus solar wind pressure, plus the possibility of prior fragmentation, will be enough to destroy it, or are more exotic interactions involved. The electric comet model, promoted by a small group of plasma physicists. Comets develop an electric charge as they interacting with the solar wind and electrical forces. This model suggests it is these forces, and not just thermal sublimation, that drives cometary activity. Mainstream astronomy has not embraced the model, finding that conventional physics adequately explains the observations without needing to invoke electrical effects, but proponents point to phenomena such as the disconnection events in comet tails and rapid changes in brightness as evidence that electrical processes do play a role. The hypothesis extends further into fringe territory, with suggestions that strong solar wind events can create charge separation in a comet's coma, cause explosive disruptions or orbital changes beyond what is expected from simple outgassing. The evidence for these claims is disputed, and the theoretical framework is incomplete, but the ideas circulate because they attempt to explain observations that do not quite fit with standard models. when Comet Atlas disintegrated during a major solar wind event. Promoters of the electric comet models saw a potential confirmation of their ideas. Mainstream astronomers found it to be an unfortunate coincidence, but ultimately a random series of events. What made the situation even more uncertain was that we really did not know what Atlas was made of. Spectroscopic observations before it disappeared were limited and did not provide a complete compositional inventory. The comet itself could have been dominated by water ice. Just like many solar system comets, it could have been dominated by carbon monoxide ice, which sublimates at much lower temperatures, and could have driven its activity at greater distances from the Sun. It could have been silicon-rich and volatile poor, more like an asteroid nucleus than a typical comet. Each composition would react differently to the heating, solar-wind interactions. If the nucleus was extremely porous, almost like an aerogel, with a density barely higher than the gas in its coma, a heat wave would have penetrated deep, warming subsurface ices, and potentially causing the entire structure to disintegrate in a cascade of sublimation. If the nucleus had an insulating dust mantle covering most of its surface, gas production would have been concentrated in a few active regions, creating jets that could have spun up the nucleus or twisted its rotation in ways that were impossible to predict. If the nucleus is a contact binary system, two lobes held together by weak gravity, tidal forces, and thermal stresses could pull it apart. The Sun, in this scenario, becomes a kind of cosmic gatekeeper, testing any object that passes through the inner solar system. Interstellar comets have formed in different environments, with structural properties that may differ from solar system comets. They might be particularly vulnerable, or they could be more robust, forged in conditions that made them tougher. We won't know until we see one take damage, or see nothing emerge. The comparison with Comet Shoemaker-Levy 9 is instructive. That comet was torn apart by tidal forces during a close pass by Jupiter in 1992, breaking into more than 20 pieces, which then slammed into the planet. In a series of spectacular impacts, the tidal disruption occurred because of Jupiter's gravitational gradient across the diameter of the comet exceeded the comet's own self-gravity, literally pulling it apart. The Sun's tidal forces are much weaker at the distance where Comet Atlas passed, but a comet weakened by thermal stress or prior fragmentation might succumb to forces that a healthy nucleus would easily resist. Did the Sun just reveal something frightening about our interstellar visitors? The answer depends on what we see when the comet emerges from conjunction. If Comet Atlas reappears intact, continuing on its hyperbolic orbit with normal gas and dust production, the solar wind event becomes a footnote, a coincidence that sparked speculation, but ultimately means nothing if the comet has disintegrated or vanished. We are left with haunting questions. Interstellar objects are fundamentally more fragile than our models assume, or whether there is something about their formation or their structure that makes them vulnerable to the Sun's onslaught in ways we had not predicted. Part 4. The vigil begins. As astronomers are marking their calendars, checking ephemerides, preparing observational plans for the moment when BAI Atlas should become visible again. The timeline depends on several factors, including the comet's precise orbit, uncertainties due to non-gravitational forces, which may have changed significantly, and the observational geometry, which determines how far the comet needs to be away from the Sun before telescopes can detect it against the background of the sky. Current predictions suggest that the comet should emerge from solar conjunction in late October or early November 2025, reaching a sufficient solar elongation, the angular separation from the Sun as seen from Earth, to be observable with specialized equipment. The initial recovery efforts will likely use space-based observatories, which can block the Sun's glare more effectively than ground-based telescopes. SOHO, The Solar and Heliospheric Observatory has coronagraphs designed to create an artificial eclipse, allowing for observation of the region near the Sun, where comets often hide. The Solar Terrestrial Relations Observatory consists of 2 spacecraft in solar orbit, providing different perspectives. Could have spotted the comet earlier than Earth-based observations. The Parker Solar Probe, humanity's closest approach to the Sun, follows a periodic orbit, taking it inside the orbit of Mercury, through regions where solar wind speeds and temperatures reach extreme values. If the probe's orbit happened to pass near Bialis during its conjunction phase, its instruments might have captured data on the comet under conditions that no ground-based telescope could observe. But Parker's scientific objectives focus on the solar corona and solar wind, not comets, and unless the comet happened to be within the probe's narrow field of view at just the right moment, we would have no data from that crucial phase. Mission scientists have not announced any such fortunate encounters, suggesting the geometry did not align or the comet was too faint for Parker's instruments to detect against the bright solar background. What will the first recovered images reveal? The best-case scenario: the comet appeared as expected, perhaps a little fainter due to dust loss, but otherwise intact with its coma and tail visible. This shows the active sublimation of ice from the nucleus. The spectral signature will show the familiar lines of water vapor, cyanogen, carbon monoxide. The molecular fingerprints confirming the comet's composition, the length and structure of the tail, will provide information about the gas production rate and solar wind conditions during the post-conjunction phase. Astronomers will measure its brightness, compare it to pre-conjunction values, and assess whether the comet lost significant mass during its closest approach to the Sun or not. The worst-case scenario: nothing appears. The sky remains empty where Atlas should be, suggesting complete disintegration. The nucleus fragmented into pieces too small to detect individually or vaporized completely, leaving only a dispersing cloud of gas, too diffuse to appear as a distinct object. This result would be disappointing, scientifically, but not unprecedented. Some comets have disappeared after a close solar approach and have been lost completely, becoming a data point in our understanding of cometary fragmentation physics. Between these two extremes lie countless possibilities. The comet could return as multiple fragments, a chain of condensations along its orbit, indicating the nucleus has split, but the pieces have survived. Debris streams are difficult to observe, as each individual piece is fainter than the original nucleus, but they provide valuable information about the nucleus's structure and the mechanics of its breakup. If Atlas returns in a fragmented state, analysts will measure the separation distance and velocity to reconstruct when and how the breakup occurred. Another possibility is a state of hibernation. The comet may have exhausted its volatile substances near the surface during its close pass by the Sun, leaving behind a dark crust that prevents further sublimation until the heat from the Sun cracks the crust, or erosion exposes fresh ice. Hibernating comets look like asteroids, showing no coma or tail, just a bare rock reflecting sunlight. If BAI Atlas enters hibernation, we would lose the ability to study its gas composition, but we would gain information about its surface processes and the formation of insulating mantles. The most compelling scenario involves a sudden brightening, as comets sometimes fragment in ways that expose pristine material, fresh volatile substances to the causing a sudden increase in gas production and brightness can create new active areas, increasing the total surface area for sublimation. If fragmentation and brightening are concurrent, the comet's appearance can be even more spectacular. The comet is gone, though in its fragmented state, it will likely fade quickly as the small pieces exhaust their ice supply. Spectroscopic diagnostics will be crucial. Pre-outburst observations showed typical signatures of water and perhaps carbon monoxide, but a complete spectral inventory was never obtained. 10 post-outburst spectra might reveal species not previously detected, either because the comet was not producing them in significant quantities, or because we were not looking at the right wavelengths. Oxygen emission lines would indicate water sublimation, and cyanogen indicates carbon-nitrogen chemistry. Sodium and iron lines sometimes appear in comets, and can be indicative. The exposure of volatile material from within the nucleus. Amateur astronomers have a role to play in the effort to restore a network of backyard telescopes distributed globally, providing continuous sky coverage that professional facilities, with their limited observation time and scheduled programs, cannot match. If Comet Atlas suddenly brightens or fragments into widely spaced pieces, amateur observers might be the first to notice. Crowdsourced astronomy is becoming increasingly important as digital cameras and software make it possible for dedicated amateurs to produce observations that rival professional quality, unfolding in real time, and anyone with a telescope and a clear sky can participate. The comet could reappear at any moment, assuming it survives, or many days, even weeks, could pass with nothing visible, until astronomers reluctantly conclude that Comet Atlas has vanished, destroyed by the sun, which it had traveled so far to visit. The uncertainty was maddening and exhilarating in equal measure. We hadn't sent any probes to intercept the comet. We had no way to actively search for it, other than aiming our telescopes at its predicted position and waiting. All we could do was watch and wonder, and prepare for whatever emerged from the glare of the sun. A broader question haunted the astronomical community. If the nucleus was gone, would we still have Comet Atlas, or was it now just debris, a scattered cloud of dust and gas? That was once an interstellar comet, but no longer qualified as a distinct object. Philosophically, it echoed the paradox of the ship of Theseus. If every plank of a ship, a wooden vessel, is replaced over time, is it still the same ship? If a comet fragments into 1,000 pieces, each piece following nearly the same orbit, carrying material from the original nucleus, are they collectively still the comet, or has the comet ceased to exist? There is no formal definition that resolves this question. It is a matter of convention and convenience, and different researchers would answer differently, depending on their perspective. But this question is important because Comet Atlas represented something precious and irreplaceable. A specimen from another star system, and its loss felt like more than just the loss of an astronomical target. It felt like losing a connection to something vast and distant. A thread linking us to the wider galaxy was severed before we could fully grasp what we were holding. Part 5. When coincidence becomes conspiracy. Why does any of this matter? Beyond the narrow confines of planetary science journals and astronomy conferences. Because humans are pattern-seeking creatures who have evolved to find meaning and correlation, to see connections even where there are none, and the simultaneous occurrence of a major solar event, the disappearance of an interstellar comet, and multiple large earthquakes on Earth has. Every alarm in our collective subconscious, signaling that something is happening. The mainstream scientific position on seismic connections between the Sun and the Earth is clear and unambiguous. Earthquakes are driven by plate tectonics, by the slow, unceasing movement of the lithospheric plates riding on the mantle, through convection that accumulates strain energy in the Earth's crust, eventually exceeding the frictional resistance between the locked faults. Solar activity. There is no plausible mechanism to trigger this release. Magnetic fields do not affect rock. Solar wind particles do not penetrate the Earth's surface. They are blocked by the magnetosphere and the atmosphere. The thermal energy provided by solar radiation is negligible compared to the Earth's internal heat. Every analysis of earthquake catalogs, searching for a correlation with solar cycles or individual solar events, has found nothing beyond what would be expected by random chance. Correlations keep appearing in the datasets, tantalizing patterns, not quite reaching statistical significance, yet not entirely disappearing. Some researchers, working on the fringes of respectability, continue to explore possible mechanisms. Could ionospheric disturbances caused by solar activity affect the electrical properties of fault zone? Could subtle changes in the Earth's rotation speed or the orientation of the magnetic field from the momentum of the solar wind being transferred? Could it adjust tectonic stress at a level too small to measure directly, but enough to tip a fault that is already near failure? Could there be a magnetohydrodynamic coupling between the ionosphere and the conductive layers in the Earth's crust, transferring energy in ways that we do not yet understand? These ideas face great skepticism because extraordinary claims require, and the evidence remains circumstantial at best. But the human mind does not operate on thresholds of statistical significance. It operates on narrative that connect disparate events into coherent wholes. When the sun erupts and the earth quakes, and a comet disappears, all within the same cycle, the narrative writes itself. Even if the physics does not hold up, the interstellar nature of Comet Atlas adds another layer of mystery and speculation. These objects come from outside our solar system, from environments that we can barely imagine, formed from materials of a distinct composition, and isotopic ratios may differ from the norms of our solar system. Literally, they are alien in the truest sense of the word, and humanity has always projected its hopes and fears onto the strange and the unknown. When Oumuamua exhibited an unexplained acceleration, not immediately attributable to standard cometary outgassing, speculation erupted about alien probes on a precise course, about technologies beyond our comprehension. The simplest explanation remains natural processes, but the probe hypothesis captured the public's imagination because it satisfies narrative needs that dry scientific papers on carbon monoxide sublimation could never touch. The disappearance of Atlas in a solar storm invited similar speculation. Was the comet carrying something encoded, something that made it a target? Were we witnessing a cosmic quarantine protocol? The sun destroying potential threats from interstellar space before they can penetrate the inner solar system. The scientific reasoning of these ideas does not lessen their psychological appeal. We want the universe to hold mysteries deeper than mechanics, orbits, and spectra. We want hidden meanings behind celestial alignments. We want comets to be more than just balls of dirty snow. We want them to be messengers, or life, or purpose. The panspermia hypothesis, the idea that life spreads throughout the universe on comets and asteroids, provides a scientific veneer for these desires. If comets carry the organic precursors that led to life on Earth, delivered during the late heavy bombardment billions of years ago, then each comet becomes a potential seed bearer, and interstellar comets become especially precious because they might carry chemistry from the biospheres around other stars. The destruction of Atlas, if that is what happened, becomes the destruction of a biological sample. A library burned before we could read its contents. More fringe possibilities circulating within peripheral communities. Proponents of the electric universe see the sun's interaction with a comet as evidence of plasma physics, which they claim mainstream science overlooks. They point to the comet's unusual changes in brightness, disconnection events, in other cometary tales, and argue that these phenomena require electrical explanations, rather than gravitational and thermal ones. The mathematics of their models rarely withstands close scrutiny. Predictions often do not align with observations, but the intuitive appeal of electricity as a universal force, the visual drama of lightning and sparks, gives electric universe ideas a persistence that surpasses their scientific shortcomings. Conspiracies inevitably arise. Are space agencies withholding data from the Parker solar probes close passes of the Sun. Did the instruments capture images or spectra of Comet Atlas during its conjunction phase that officials chose not to release? What would motivate such secrecy? Perhaps the comet exhibited unexplainable behavior, challenges fundamental assumptions, frightening those who understand the implications. Perhaps it, in a way inconsistent with natural processes, or emits a signal, or alters its trajectory in ways that suggest control. These scenarios are extremely unlikely, almost impossible, but the absence of evidence becomes evidence of conspiracy. In a mind inclined to distrust official narratives, the psychological function of conspiracy theories has been well studied. They provide control, or the illusion of control. When faced with random and chaotic events, they replace a universe of meaningless coincidence with one of hidden order and purpose. Even if that purpose is malevolent, it is better to believe in a conspiracy than to accept that earthquakes happen randomly, that comets disintegrate for no reason, that we are tiny specks of consciousness on a fragile world, hurtling through an indifferent universe. The narrative of hidden knowledge and suppressed truth is emotionally satisfying, more a narrative of patient scientific investigation, slowly converging toward tentative conclusions. But here's the thing. Sometimes the universe aligns in challenging ways. Sometimes a coincidence is too perfect to be dismissed, even when we cannot establish a cause. The confluence of events in October of 2025, the solar storm, and the disappearance of the comet and the earthquake, could be precisely that. A coincidence so unlikely that it demands our attention, even if it ultimately, or it could be the first hint of connections that we do not yet understand. Faint couplings between geophysical systems and space weather, operating at levels beneath our current thresholds of detection. Science progresses by investigating anomalies, not by dismissing them. The researchers exploring the solar earthquake correlation are conducting legitimate science. While speculative, they may find nothing, but the search in itself is worthwhile. When Comet Atlas emerges from behind the Sun, we may not recognize it. The comet that goes in may not be the comet that comes out. And when astronomers publish their analyses about what they observed, when they presented explanations based on physics and chemistry and orbital mechanics, some would accept those explanations and move on. Others would continue to search for hidden meaning, for connections between comets and earthquakes, and solar storms that transcend physical cause. Both reactions are human. Both reflect deep needs to understand our place in a universe that offers more questions than answers. The Sun did something frightening and a comet disappeared, and the Earth shook, and whatever truth lies beneath those events, we are left with equal parts wonder and unease. Part 6. Comets we can see. While Atlas played hide-and-seek behind the Sun, another comet was putting on a show that you could actually watch, assuming you knew where to look, and you were willing to wake up before dawn, or stay up late after sunset. Comet C202 5A6 was discovered by the Mount Lemmon Observatory in Arizona, and therefore carries the designation Lemon. It was approaching its own close encounter with the Sun and reaching apatus within range of binoculars or a small telescope, possibly even naked-eye visibility for observers under dark skies, far from light pollution. The next 2 weeks represent the optimal viewing window, as Lemmon's perihelion, its closest approach to the Sun, is scheduled for mid-November 2025. But its orbital geometry, which gives it maximum visibility from Earth, occurs just before perihelion, when it is still far enough from the Sun's glare to be observed comfortably. The comet is currently visible in the eastern sky, rising a few hours before the Sun. It glows with the soft, fuzzy light characteristic of a comet, active with a well-developed coma, and, yes, possibly a short tail. Current brightness forecasts place Lemon between magnitude 4 and magnitude 5, right on the threshold of naked-eye visibility. The human eye can typically see objects down to magnitude 6 under good conditions, and a magnitude 4 would be easily visible far from city lights, although locating it, without binoculars, requires knowing exactly where to look. The comet is currently passing through the constellation of Cancer, moving eastward against the background stars, and Finder chart are available online showing its path relative to recognizable star patterns. Observing comets requires patience in a dark sky. Unlike planets, which appear as distinct points or disks, comets are diffuse objects, their light spread out over an extended area. This diffuse nature makes them more sensitive to light, pollution, and sky conditions, compared to compact objects of a similar total brightness. A comet of magnitude 4 will completely disappear in a bright suburban sky, where magnitude 4 stars are still easily visible. Success requires moving away from urban areas to locations where the Milky Way is visible overhead, where the darkness of the sky allows your eyes to detect objects with low, extended surface brightness. Binoculars are the ideal instrument for comet watching, as they provide enough magnification to concentrate the comet's light, while still maintaining a wide field of view, which makes finding and tracking the object easier. 7 by 51 binoculars, a common size owned by many amateur astronomers and nature observers, work particularly well. Mount them on a tripod if possible, to eliminate handshake and allow for longer viewing times. The comet will appear as a small, fuzzy patch, distinctly different from a star, perhaps with a hint of green. From the emission of carbon molecules, diatomic in the coma, a telescope can reveal more detail, showing the structure of the coma, any jets or fans of material emanating from active regions, on the nucleus, and the tail if one has developed sufficiently. But higher magnification narrows the field of view, making the comet harder to locate initially, and more difficult to keep centered, as the Earth's rotation carries it across the sky. Many experienced comet observers prefer binoculars for aesthetic reasons. The wide field of view shows the comet in context against the star fields, emphasizing its nature as a temporary visitor, moving through the more permanent celestial landscape. Initial observations of Lemon revealed something that made comet scientists both nervous and excited in equal measure. Its brightness was not following the models predicted perfectly. Comets are famously unpredictable, as their brightness depends on factors that we cannot measure directly, such as nucleus size, composition, rotational state, surface properties, and the dust-to-gas ratio. The models make assumptions about these parameters based on statistics from other comets, but individual comets often deviate from the average behavior. Lemon showed phases where it brightened more rapidly than expected, followed by plateaus where its brightness was nearly constant, despite its ever-decreasing distance to the Sun. These deviations could indicate several phenomena. Outburst activity, where the sudden exposure of volatile material, fresh volatiles, creates a temporary increase in gas and dust production, which can cause a rapid brightening. The rotation of the nucleus brings different hemispheres into the sunlight. If one hemisphere is more active than the other, creating periodic variations in brightness, or more ominously, the deviations could signal the early stages of fragmentation, where the nucleus begins to break apart under thermal or tidal stress. Fragmentation is a potential danger that haunts every cometary prediction. A comet might brighten normally, following its expected curve toward perihelion, looking healthy in every respect, and then suddenly it begins to disintegrate. This process can be rapid or gradual. Sometimes a large piece breaks off and forms a separate condensation, visible near the main nucleus. Sometimes the entire nucleus disintegrates into a cloud of small fragments, which are individually too faint to see, but collectively can produce a significant increase in total brightness, as their total surface area promotes enhanced sublimation. The physics of fragmentation involves mechanical strength, thermal stress, and rotational state. Comet nuclei are weak structures, more like compressed snow than solid rock, held together, primarily by their own feeble gravity, supplemented by tensile strength from freezing, and possibly organic tars. When the sun heats one side of the nucleus, thermal expansion creates stress, and if the nucleus is rotating, centrifugal force adds to the mechanical strain, and jets of gas create torques that can spin the nucleus faster. At some point, the accumulated stress exceeds the material's strength. Cracks propagate and the nucleus splits apart. The sublimation science of Comet Lemon adds another layer of complexity. The comet appears to be driven by the sublimation of carbon monoxide, or carbon dioxide, as much as or more than the sublimation of water. These molecules are more volatile than water, meaning they transition from a solid to a gas. At lower temperatures and at greater distances from the sun, a comet driven by carbon monoxide can become active far beyond the snow line, where water ice remains frozen, creating a coma and tail while still in the outer solar system. As the comet approaches perihelion and temperatures rise, eventually becomes dominant, often creating a transition in activity patterns. The interaction of the tail with the solar wind provides another observational opportunity. Lemon's ion tail, if it develops one, will point directly away from the sun, blown back by the solar wind like a windsock. The dust tail follows a curved path, its particles pushed away by solar radiation pressure, but still retaining the orbital motion they had when released from the nucleus. These two types of tails, ion and dust, often separate into distinct structures, visible in photographs. The ion tail has a slightly blue color from the emission of carbon monoxide ions, is straight and sometimes features bands and knots caused by irregularities in the magnetic field in the solar wind. The dust tail is white and yellow from reflected sunlight, broader and more diffuse, curving gently away from the nucleus. Comparing Lemon with Atlas highlights the fundamental differences between comets native to the solar system and interstellar visitors. Lemon formed 4.66 billion years ago in the disk of gas and dust surrounding the young sun, perhaps in the region beyond Neptune, where temperatures were cold enough for water and other volatile substances to condense into ice. Gravitational perturbations from the giant planets eventually scattered it into the Oort cloud, a vast, spherical reservoir of comets surrounding the solar system at distances up to 100,000 astronomical units. Something, perhaps the gravitational influence of a passing star, or a molecular cloud, giant, perturbed Lemon's orbit, causing it to fall back toward the sun. On the journey we are observing today, its composition reflects the primordial chemistry and molecular abundance present in our local region of the galaxy 4 billion years ago. So Atlas formed elsewhere, around another star, under conditions that might have been similar or fundamentally different. The temperature and pressure in that protoplanetary disk, the abundance of heavy elements, the radiation environment, the timing of planet formation, all these factors influence the composition and structure of a comet. By comparing interstellar comets with our solar system's comets, essentially, we are comparing samples from different stellar nurseries, looking for commonalities, revealing universal processes and differences, highlighting local variations. Lemon serves as a real-time reminder of just how fragile comets are. Every comet is a gamble against disintegration. Most survive their perihelion passage, losing some mass to sublimation, retreating back to the outer solar system or beyond, and remaining intact. Some fragment significantly, offering spectacular displays, as multiple nuclei and expanding dust clouds brighten and then fade, some disappearing completely, so thoroughly destroyed that tracking them later becomes impossible. Observing Lemon during its peak viewing window is not just about enjoying a beautiful celestial sight. It is about witnessing a survivor, an object that has endured billions of years in the deep freeze of the Oort cloud, and is now racing through a gauntlet of heat and solar radiation, which may or may not end in its destruction. The timing is fortunate. While Comet Atlas hides behind the Sun, Lemon provides an alternative target, another comet, that we can actually observe and study. If you have never seen a comet, if you have only encountered them as images on a screen or diagrams in a textbook, now is your chance. Go outside before dawn, find a dark location, let your eyes adapt for 10 or 15 minutes, and scan the clear eastern sky in the constellation Cancer. That faint streak of light contains ice formed before the Earth existed, organic molecules that predate life, silicon dust older than our planet. You are seeing a messenger from the dawn of the solar system, and in 2 weeks, it will fade from view. Its brief moment of visibility ends while its fate, whether to survive or disintegrate, is not yet written. Watch the skies now, while Atlas is in hiding. Part 7, The Swan and the Setting. Comets tend to arrive in clusters, or at least that is how it seems, to the observers who track these icy visitors. The reality is less poetic at any given time. Countless comets orbit the Sun at many different distances. Most are too faint to be observed without a large telescope. A few are bright enough to capture the attention of amateurs, and very rarely is a comet spectacular enough to become visible to the naked eye and enter the public consciousness. The clusters that we perceive are a result of observational bias and the nature of statistics, the statistics of comet discoveries, but they still create periods when observers of comets have many targets to choose from. 2025 is shaping up to be one of those periods, with Lemon and Atlas having faded away. Another comet, designated C/2025R2 Swan, has entered the Swan list, which refers to the Solar Wind Anisotropes instrument on the SOHO spacecraft, observing the sky in ultraviolet wavelengths sensitive to hydrogen emissions. Comets produce enormous clouds of hydrogen atoms, created when water molecules are broken apart by solar, ultraviolet radiation. These clouds are invisible to optical telescopes, but they glow brightly at specific ultraviolet wavelengths in particular, and Swan can detect them from a great distance, sometimes spotting comets months before ground-based observers do. Comet C/20 was discovered through its hydrogen corona, the giant, invisible cloud surrounding its visible coma. Follow-up optical observations confirmed the discovery and allowed for a preliminary orbit to be calculated. The comet is following an elongated elliptical orbit, which will bring it to perihelion in early 2026, long after Lemon's close approach, but early enough to maintain the interest of observers. Comet observers were preparing their equipment and their observation plans. Initial brightness estimates for Swan suggested that it might reach magnitude 6 or 7 at perihelion, making it a binocular object, but perhaps not visible to the naked eye, except under exceptional circumstances. The predicted brightness depended on assumptions about the nucleus size and its level of activity, both of which remained uncertain. Discovered by Swan had exceeded expectations, brightening significantly as they approached the Sun. Other comets had been disappointing, remaining faint and diffuse. Despite hopeful predictions, the only way to know was to watch and wait. One intriguing possibility involved new comets creating meteor showers. As a comet approaches the Sun, it sheds dust that spreads along its orbital path, creating a stream of particles. If Earth's orbit intersects this dust stream, the particles slam into our atmosphere at high speeds, typically 30 to 70 kilometers per second, and vaporize in streaks of light we call meteors. Most of the meteor showers that we observe annually, such as the Perseids in August or the Geminids in December, are the result of the Earth passing through trails of dust that have been formed by comets that have made multiple passes through their perihelion, depositing dust over centuries or millennia. New comets making their first pass through the inner solar system. can create unpredictable meteor activity. The dust distribution along their orbits has not been smoothed out by repeated passages and planetary perturbations. Fresh ejections can create dense clumps of particles. If the Earth happens to pass through one of these clumps, the meteor rate can increase dramatically, creating a meteor storm, or thousands of visible meteors per hour. These events are rare and difficult to predict because they depend on the precise distribution of dust in space, which we cannot measure directly. The orbit of Cygnus will be precisely calculated in the coming months, and astronomers will determine if there are any potential dust stream crossings with Earth. Whether it could happen or not, even a slight chance of a meteor shower is enough to fill comet enthusiasts and meteor watchers with excitement. Witnessing a meteor storm is an unmissable experience, a celestial fireworks display that occurs perhaps once or twice in a generation. Meteors radiate from a single point in the sky, known as the radiant point, converging. These are lines of perspective created by the particle trajectories entering the atmosphere in parallel. During a storm, the entire sky seems to rain meteors. Streaks of light appear in every direction, overwhelming the senses in a way that photographs can never fully capture. But for every comet that brightens and performs as hoped, others simply fizzle out. The history of cometary astronomy is filled with failed predictions, with objects expected to become great comets, which instead remain dim and unremarkable. Comet Kohoutek in 1973 was predicted to become one of the brightest comets of the century, but it barely reached naked eye visibility, disappointing millions who had been promised a spectacular display. Comet Eisen in 2. One comet was thought to survive perihelion and brighten considerably, but it disintegrated instead. These failures teach us humility and remind us of how much we have yet to understand about cometary physics. The comparison between the light curves of Swan and Lemon will ultimately provide useful scientific data. When two comets are observed simultaneously under similar solar conditions, it allows for a direct comparison of their activity levels and sublimation physics. Differences in their brightness at comparable distances from the Sun can indicate differences in nucleus size, composition, or the nature of their surfaces. If one comet is dominated by water and the other by carbon monoxide, their activity profiles will diverge in characteristic ways. If one comet fragments and the other does not, we gain clues about the structural differences that determine susceptibility to fragmentation. Using Swan and Lemon as counterpoints creates a narrative tension. Many comets fail. So will Atlas fail too? Is there something about the solar environment presently makes the comet's survival less likely, does it not? The coronal whole event of October 2025 could be a one-time coincidence, or it could signal a period of intensified solar activity that threatens any comet passing through the inner solar system. The Sun's 11-year activity cycle is approaching its solar maximum, the phase when sunspots and coronal mass ejections become more frequent as solar wind speeds and magnetic field intensity increase. Comets approaching perihelion during solar maximum face harsher conditions than those arriving during the solar minimum. The history of cometary fragmentation provides sobering statistics. The tidal disruption of Comet Shoemaker-Levy 9 by Jupiter in 1992, followed by the spectacular impacts in 1994, demonstrated just how completely a comet can be destroyed by gravitational and tidal forces. Comet 73P Schwarzmann-Wachmann 3, which fragmented during its 1995 appearance, broke into multiple pieces that have separated over the following years. By its 2001 return, a comet had broken into more than 60 identified fragments, a debris field stretching along several thousand kilometers of its orbit. Some fragments remained active, creating small comas, while other fragments appeared dormant. Their volatiles either depleted or sealed beneath crusts of inactivity, are important for predicting space hazards. A single, large cometary nucleus poses a minimal risk to Earth because the probability of a nucleus several kilometers wide striking our planet is extremely small. Fragments creates tens or hundreds of pieces, each one potentially entering the atmosphere, and while the individual fragments are smaller and less destructive than the original nucleus, the probability of one of them crossing Earth's path increases. Most cometary fragments burn up harmlessly in the atmosphere or miss Earth entirely, but the risk calculation changes when you are dealing with scattered debris instead of a single object, predicting the event of Comet 67P, predicted to be the brightest comet appearance of the century. Placing current observations into context, comets are the chaotic clocks of the solar system, appearing unpredictably, brightening, and often fragmenting without warning. They mark time in human consciousness differently, compared to the regular movements of the planets and stars. One generation remembers Halley's Comet in 1986, a disappointing sight for most people, but culturally significant. The previous generation remembers Comet Hale-Bopp in 1997, visible to the naked eye for many months, bright enough to be seen from city centers. The current generation might remember Lemon, or Swan, or Atlas. If any of them had survived and brightened enough, are we in a period of clustered appearances, of unusual comets? No, statistical analysis of the rate of comet discoveries over the decades shows that fluctuations could represent real clustering, or simply reflect improvements in detection technology. More telescopes scan more of the sky with greater sensitivity, naturally finding more comets. The Atlas project discovered Atlas. Atlas exists specifically to find near-Earth objects and find comets as a bonus. The Catalina Sky Survey, the Mount Lemmon Observatory, Pan-STARRS in Hawaii. All of these automated systems continuously track anything that moves, and comets move. But there is a fascinating hint in the data that the distant Oort cloud, that reservoir of comets, may experience disturbances, sending showers of comets falling toward the inner solar system, passing stars, gravitational interactions with giant molecular clouds in the galaxy, even the vertical oscillation of the solar system through the galactic plane as it orbits the center of the Milky Way. All of these things can dislodge comets. If these comet showers are real, they would occur on timescales of millions of years, too long to be observed by direct human detection, but buried in the geological record. Evidence of impact clustering could reveal these ancient comet storms that battered the inner solar system during the age of the dinosaurs, or even earlier in Earth's history. The comets act as the chaotic clock of the solar system, precisely because they do not follow the regular, predictable paths of the planets. Most planets orbit on paths that are nearly circular, centuries in advance with high precision. Comets arrive from the outer darkness on highly elliptical orbits. Their return periods, if they return at all, span decades, centuries, or millennia. Some are new visitors, falling in for the first time from the Oort cloud. Other comets are short-period comets, captured by Jupiter's gravity into orbits that bring them back every few years. They remind us that the solar system is not a clockwork mechanism of perfect orbits, but a chaotic, dynamic environment where interactions of gravity constantly shuffle orbits, and new players enter the stage. Part 8, The Unbreakable Signal. While astronomers scan the skies, searching for comets and monitoring the solar wind, a different kind of race, a cosmic one, unfolds in laboratories and ground stations here on Earth. In 2025, China announced the completion of a link for quantum communication that is the longest in the world, a network of 12,900 kilometers connecting Beijing with remote ground stations via satellite relays, and declared that the system provides data transmission that is truly unhackable. This announcement represents a milestone in the quantum information revolution, and if the system works as advertised, it will change the landscape of global communication and network security in ways that go far beyond immediate military or commercial applications. Quantum key distribution. The underlying technology harnesses the fundamental properties of quantum mechanics to detect eavesdropping. The fundamental principle is both elegant and strained. Information is encoded in the quantum states of photons, single particles of light, which are transmitted through optical fiber or through space between satellites and ground stations. The quantum no-cloning theorem ensures that these states cannot be perfectly copied. Any attempt to measure or intercept the photons will necessarily disturb them in detectable ways. This means that two parties sharing a quantum communication channel can generate an encryption key and know with certainty. Has anyone tried to intercept those keys during the process of transmission? The process begins with entangled photons, pairs of particles created simultaneously and sharing a quantum connection, so that measuring the properties of one photon instantly affects the other, regardless of the distance separating them. This phenomenon, which Einstein famously called spooky action at a distance, has been verified in countless experiments and forms the basis for several quantum technologies that have been proposed, including quantum computing, magnetism, and quantum teleportation. For quantum key distribution, the photons that are entangled allow two parties to establish random numbers that are shared and can be used as encryption keys. The hardware implementation requires extraordinary precision. The photons must be generated entangled, transmitted, and detected with minimal loss and maximum fidelity.